Hello, everyone. Today we're going to take a look at the deep learning with keras done in R and to give you an example on classification first. The example is what we are very familiar with. It is arrays or the flower um, data set with the base R. So we don't have to worry about the where to get the data. Let's room in to the R Studio and take a look at the um, script. And this program, before we run this, I assume you already installed the keras and TensorFlow on your computer and ready to run. And if you're struggling with these installations, I have a separate video you can refer to and play with it. You may Google a little bit and you will get there and to write every step through. Well, this code include three parts. One, and the first step is to uh, kind of reformatting your data and to transform it into a matrix um, format and for the TensorFlow in the background. And then we will build up the model first and just use a three layers deep uh, learning a very typical configuration here. And we use a reload and in the first two layers, and then we use the softmax to um, differentiate these three types of flowers. And this is the kind of a typical of the typical very dry bone model before we run more models and to compare these models. Then we have another one with the dropout, and that's the purpose of this is to reduce the overfit. You can imagine this data set only has about 150 rows, so you have these very few uh, like data observations. Then you use a deep learning network trying to predict the three types of flowers. You face a very challenging task, and you're overfeeding. You're kind of have too many flexible parameters. You may get a very good accuracy from the beginning, but for the test set or for the unknown um, um, input, you may give a very poor prediction. So this is one of the techniques you can reduce overfitting. So let's run this code and load the keras library. And we also want to use um, uh, correct package to compare the model performance. Let me correct myself. First, let's load the keras um, library. Then we load the correct library. Then we take a look at the data set. Um, as you can imagine, the species or the type of the flowers, we may have to get this part as a feature input into the TensorFlow and as a matrix, and then treat this um, a column separately as a label and in the following sections. So let's do and split the data, and then we use the data matrix to transform the selected features as we mentioned, and we also separated the target. And let me um, check it again. Well, we have 105 data lines for this training set. Um, as we know, we have to use the dummy um, representation to do the uh, kind of a factor or the uh, kind of a different species, and then transfer them in a format with like a 0, 1, 1 or something like that in order for the model to accept. So let's continue to run this. We have a summary. Um, well, the we also can take a look at the training features. Um, Eventually, we have to transform them and scale them in order for the neural networks to accept it. Typically, the scale or the scaling factor is quite important prior to the uh, input to the neural networks. It's different than the other classic models like the trees, the random forest, or the other kind of traditional models. So that's one. That's a kind of the data preparation step, and the most important thing is you have don't forget to transfer or transform them into the matrix format uh, before you can feed the data into the model. Let's take a look at the model first, and without kind of any additional feature, just a dry bone deep layer networks. Well, let's build the model. It's a kind of a structure skeleton. It has three layers, and it has three how to say it, types of the labels you want to predict, and that's a summary of the label. You can imagine it has a total 193 parameters. Uh, that's kind of these all these variables in this neural network. You can change to predict the what type of the flowers or the classifications you can do. But remember, we only have 105 observations. So you can imagine the overfitting could be very challenging for this. And it is real, it can give you a very, very misleading results. Well, let's compile the model. For the loss, that's the cross entropy we selected, and also we use um, optimizer. That's very typical for the classification. We use the accuracy, to evaluate the performance of the model. So we're going to split it 9 to 1 further within a training set. So when it runs one epoch, like a one iteration, and it can give you some indication what's the uh, performance for the training, as well as a little a few lines, a few observations of the data to validate the model performance. It will run the big loop 200 steps, and the other parameters related to how to optimize uh, the losses, or how to converge, how to make the model converge faster. Well, let's run the model. Since this is an extremely small data set, it will take a few seconds to finish this. Well, you can see on the right side of the panel, these the data set um, can have different criteria for the. You see the losses supposed to be the smaller the better. We can see the validation loss is a higher when it runs into uh, more and more steps. And we can also see the validation accuracy after 50 big loops, and it is below. We can almost say after 50 or 60 epochs, and there's nothing more you achieve, or you improve the model. Maybe we can select the 60 steps and kind of roughly to define a model. So we have the 80, 82% accuracy on the validation set. Remember, that's the 0.1 and percent 0.1 or the 10% of the training data set. And on the other around 90, 95 observations, you can achieve 93.6% accuracy. So that's just a kind of a first shot run. Don't take it too seriously, and you need to run multiple models to verify your model whether it makes sense or not. Let's plot the model. It gives you the overall accuracy and the losses along the loops. And well, you can see it has some train, and then it's kind of a plateau, achieve the plateau a little bit. And as we say, we probably can cut it off 75 um, epochs, and before we stop the model. Well, let's evaluate it on the. Remember, we have the other 45 observations we can test. So, surprisingly, I give you almost 98% accuracy. As I suggested before, you don't take this too seriously. You need more runs to consolidate your conclusions. And then let's run another model trying to